Hi, everyone. I'm very excited to be here with you today, especially since this is my very first talk at the conference. I'm Szaka from Whitepages, and I'm going to talk about the challenges of our journey at Whitepages of migrating an existing RDD-based application to Spark SQL. So this is going to be a developer-focused talk. I'm going to talk mostly about type safety. So how many Scala developers are here in this room? Okay, so the target audience is pretty what I expected. Great. Before diving into the topic, a brief introduction. So who has heard of Whitepages before? Any of you? So we are a software company. We're not printing phone books. We have a graph database of over 4 billion identity records that would be information about persons like their names, gender, date of birth, etc., and contact points like addresses, emails, and phone numbers. We have two business lines: a consumer application that is, what you can reach via our website or mobile app, and the other one is a business-to-business solution. We are providing fraud prevention and identity verification of services for enterprises. We have search services backing both of these business lines that serve more than 2 million queries a day, and the whole thing is backed by our identity graph database. I'm working at the data ingestion team at Whitepages. We have this big graph database of over 4 billion entities and 6 billion links between them. And at the data ingestion team, we are dealing with maintaining the pipeline that ingests our upstream identity providers' data into our graph database. This is a usual batch workload, so we get these flat files, mostly flat files. And we are dealing with the usual cleaning up transformation steps. But it's also more complex than that, because talking about a graph database, we also have to do this, creating subgraphs, merging, resolving conflicts, etc. So this is a pretty complex application at the end, consisting of more than 30,000 lines of code. And it was written using RDDs. And it was a pretty conventional application, what you might expect from a batch Spark application. So RDDs, we domained our types in form of case classes. We have a huge domain of over 30 case classes. And functional transformations and flat map, all you can think about. But after a while, so this application was chugging along well for some time, but after a while, we started facing performance issues first. So the build times were slowly degrading. We had to wait more and more for our data builds. Then cluster failures and other unreliability started to turn up their heads. So we had to stop and think about the source of these problems, and we figured out that there were a lot of infrastructure problems, code bugs, even in our business logic, or distributed code bugs like unperformant code that is very heavy on shuffles. But we found out that we had a lot of these short-lived objects living in memory, a lot of very heavy GC cycles, and all of this stuff together. So basically, we were reaching the limitations of Spark itself in terms of what it can do with RDDs of JVM types. And we figured that we could fix some performance bugs by migrating to Spark SQL, basically. So we knew that this won't be a silver bullet, but it could help alleviate a lot of our problems we were facing. So these were basically mainly promises that could be solved by switching to Spark SQL. I'm sure you know of Tungsten and Catalyst and all this stuff. I don't have to introduce it for you. So optimized memory and optimized runtime and a higher level API for writing distributed code, which is more concise and less prone to performance bugs. Basically, these are the promises. So we did a basic experiment by just blindly writing our code to dataset. So not not really caring about performance, not really caring about using selects and all these untyped data frame operations, leaving the maps and flat maps and all, all the stuff there, just to get a quick view. And we achieved 20% speed up even with this. So we determined that we are going to do a production quality code migration. We had some additional requirements. So of course we had these requirements of some level of speed up, resolving these issues with the out-of-memory errors and these failures. But we also wanted to keep the compatibility. We also needed to actually keep compatibility with our existing formats. We could not change the schema of our domain types. And of course, at that side of the code base, we wanted to continue using Scala, continue using type-safe code. So, we think that idiomatic Scala is type-safe Scala, basically. So we didn't want to use a very untyped API for dealing with transformations. So, but on the other hand, we didn't want any compromise to performance, and that means leveraging a Catalyst query optimizer to its full potential, and basically not having this serialization, deserialization, and optimization barriers that come with using lambdas. So. The next two slides will be about debunking some myths and misconceptions that are usually faced when we actually first heard about the DataSet API 2 years ago. So these tutorials and blog posts focus on, so they paint this picture that you have these three basic APIs that you can use, DataSets, DataFrames, and SQL API, and that they have a decreasing amount of type safety. Being DataSets the most safe, offering the most safety guarantees. But the catch is that they have these optimization barriers when you use lambdas, and they are slower. So first of all, is this true? So when we started to think about it, how come that their DataFrames and DataSets are two different APIs? This doesn't make sense. DataFrame is a type llas, so it can't have behavior attached. So how is this an API? And what we started to basically figure out on ourselves that, you have dataset rows which are untyped, so the rows are untyped, and the transformations that transform the type dataset into another type dataset are basically those ones that are the, what we should consider as the part of the DataSet API. So if something returns a dataset of T, that should be the part of the DataSet API. The other ones are not. So let's see what operations do we have as part of the DataSet API. Above the thick line, we have these operations that accept lambdas and do the transformation in Scala land. And these have those barriers that are often discussed. Optimization barriers and the serialization, deserialization cost. But the methods below the thick line are still DataSet API methods, but they don't have any of these. So for example, join with. It accepts a dataset of T and a dataset of U and returns a tuple of dataset T and U. But it doesn't do anything with Scala code. So, and the other ones below, slightly less interesting because they don't modify the schema, but they are part of the DataSet API too without performance costs. But some of them have other problems. So you can see that they have untyped column referencing, which means that they are not type safe. You can still have an error in the column name. You can still face an analysis error. So basically, there are two problems with the DataSet API. Some methods have performance problems. Other methods have type safety problems, despite the common belief. And actually, there's a third problem. That is, creating a data set you cannot create a data set of an arbitrary type. There are a predefined set of types that are supported out of the box. So the set of methods the set of types that are supported are the set that have these encoders defined. So these encoders are basically define the behavior of shifting between the JVM and the tungsten realm, and they are required, strictly required, to have a data set of T. Whether you are using lambdas or not, it does not matter. So we have these primitive types in purple. Basically, we have some few others, booleans. I think that's the only thing that's left. And we have these recursive types in blue. And so of course, the recursive type can contain the recursive type themselves and the primitive types in arbitrary nesting, so you can have a product of an option of a floating point number. But what if you want to have an API, a data set of an arbitrary type that is not supported? You will have a compile time exception. And well, basically, how can you work around this? If you have a lot of types, you have an existing class hierarchy, you can have a type like this deeply nested in a structure. What can you do? Well, obviously, rewriting this to dataset compatible types does not solve very much, because you will write a boilerplate. And also, if you are doing some computation in Lambda, you will create additional overhead for the garbage collector, because you will then have this mappable type, then you will be converting to your real domain type. So this is not a solution. The real solution is, of course, writing an encoder for this type. Here is an encoder. So this does not show the imports that are required from the internal Catalyst APIs, but it shows that you will have this expression encoder, that you define the schema of it. This is how the SQL looks like. You can see that this is a struct of two longs, most significant bit and least significant byte. And you will attach this serializer and deserializer instances, which are basically created by this DSL that assembles the Java expression responsible for the conversion. So, yay, this will compile and it will work. This is very good. You achieve to add a new type that works. But what if you put this type nest this type into another type? For example, tuple. Tuple is supported because it is a product. It's supported out of the box. What happens? Who thinks that this will compile? Hands up. Who thinks this will compile? This will compile. Who thinks that this will run? Nobody. Great. It will not run. It will cause an analysis exception. No, sorry, not an analysis exception. It will occur during runtime. It will occur in analysis time, sorry. So this stack trace points to the Scala reflection API. Let's see what happens. So we basically added this UUID type, but it has no connection to the other types. Why? Because here, how it looks like in Spark, you have this product that finds an expression encoder, that finds a Scala reflection serializer, and that will have basically hard-coded values of cases, which it supports, and obviously you won't have the case for the UUID, which means that this API is not extendable. What can you do? Remove the barrier and handle these types uniformly. How should you do that? Rewrite from scratch. This doesn't require changing Scala internals, actually, because these are very kind of separate part, well separated from Scala internals. You can just copy much of the code happening here and rewrite it in your own generic framework, however you want. So one thing you can do is just use runtime reflection, but have some kind of way for registering types. But as we like type-safe programming and we like Scala, we would like to do it in a robust type-safe way, and that is basically doing it with shapeless. Who knows shapeless? Some people, yeah. Okay. So shapeless is a generic programming library for Scala, and it basically has a lot of few abstractions for dealing with RDDs and changing representation. So it can change a product, so it can encode an arbitrary product in a type-safe manner in which you can iterate this product. So this abstraction is HList, a heterogeneous list, which can encode type safely a product that you can iterate, that you would iterate a list, basically. And you can add arbitrary behavior to an arbitrary product. So this is how you would, how it would look like if you write it. So we create this typed encoder type class, and we have these primitive type encoder instances for our primitive types. It would be very similar how it looks like internally, but these recursive types would rely on implicit resolution, recursive implicit resolution. The compiler will find a typed encoder T for the sequence of T. So basically, when the compiler encounters this typed encoder, the requirement of typed encoder of a tuple of UUIDs, it will find this product encoder, but that would require this typed encoder of UUID, and that is defined as well, so it will find it, and this will compile, and the correct behavior will be assembled. But if any of these steps fails, it will return a compile time error. So basically, this is how it is done. To be completely honest, it wasn't our idea. This is this library, Frameless. It's open source. You can find it on GitHub. And these have these customizable type-safe encoders that you can use in your application. Okay, let's go on. One other feature you can use is multiple encoders. For example, for UUID, you can have a string representation as well as 2 longs. And the idea behind this is you can use a string to store it in a database, but it's large for memory storage. It's easy to inspect. It's easy to handle for SQL, for example, for humans if they want to manipulate it. But it would be much better to encode this as 2 longs if you are shuffling a lot of this around internally in a Spark application. So what you can do is create 2 different encoders and choose what you import, basically depending on what your usage is. Some other features that can be added to help automatically deriving meaningful classes. Spark has this schema inferencing by default. It can infer the schema for your input. But what if you want to validate your schema? What if you don't want to pay the schema inference cost? You can specify the schema manually by yourself by creating this struct type. Better solution would be to derive it from the encoder. So you are dealing with datasets, you have this encoder for it, you can add the schema there for your encoder, and this is going to validate it. But oftentimes we found out that we do not want to model the shape of a flat CSV file. A lot of times they have nested information or repeating information encoded in them because you cannot encode nested structures into CSV. So we added this extension. You can nest. Basically, you can add this annotation to case classes, and it will try to nest the properties that can be found for that case class. And it works for classes and works for sequences. And you can find it in this repository. So that's the first thing. Now, what if, so the second thing is, I'm rushing, operations with type safety problems. So what can you do with them? So the first thing to do is be less ambitious towards it and don't really want to achieve type safety. Just want to have expressive types on function boundaries. So you can break down your Spark code into functions that are meaningful and reusable and pass along data sets along them. You can if you have the encoders, but inside the functions, use untyped operations. And basically, this is not type safe because analysis exceptions can, of course, occur, but it at least documents your types. So, for example, if you have somewhere an error that will propagate as long as this line, so it won't propagate into another function, downstream function using it, it will be code there, which kind of confines the scope of the problem. Of course, the real solution is to use something that has a typed API for the data frame operations, and Frameless has support for it. These are the main features of Frameless, actually. So you will have basically typed support for all of the major operations on data frames. Let's see. For example, you have this data frame stuff, which is not very optimal. I mean, it would not be optimal if it were encoded as data sets, because if there were optimization barriers, then the filters would happen after the select and could not be pushed down to Parquet reader. Anyways, this is data frame, so this is optimal. This can be optimized, but it has an error, a typo, and it will result in an analysis exception, a runtime error. So you can encode this using typed data sets from Frameless, and this will be perfectly typed. So even if the properties of this wouldn't be aligned with the properties here, you would get a compile time error, and you will get a compile time error when you're trying to access a column that is not defined on the data data frame. And the nicest thing is that you will have an optimized plan, so it won't have any cost. Okay, what can we do with operations with performance problems? So that's the Lambda stuff. We have this issue, we have this ticket in the Spark issue tracker. So developers of Spark came up with this idea of compiling simple closures to catalyst expressions if you have very simple selects, maps, group, filters, whatever, then it could analyze the bytecode, the generated bytecode of it, and try to match it along some patterns to create the corresponding data frame operation. So this would result in both of these having the same optimized plan. But sadly, this is not implemented, and this issue is pretty stale. It's stale for a year now. So basically, we cannot do much about it. What can we do to somehow mitigate the problem if we need to use UDFs? So we have some custom processing that cannot be changed. Well, one of the things we can do is to use this UDF function, but yeah, it basically can help you if you have a large data frame. I mean large, meaning having a lot of columns, but you only have to process one column at a time, and you don't want to serialize all that columns for processing that only one. So the problem with this, there's an issue with Spark that this does not work for somehow. This is a bug. So it will throw this class exception. It will throw this for any kind of nested stuff. So it will only work for primitive types for some reason. But one of my colleagues, Gabor, written a workaround for this. He published it in this typed UDF library. You can just use this typed UDF class and use it the same way you would use a UDF, and it will work for nested structures as well. So basically, lambdas only use them if really needed and face the consequences. So that was my talk, basically. The takeaways are, well, this stuff is hard. So if you want to keep the type safety of your existing RDD application, you want to keep the types, the existing domain types and all that, that this will be work, but some libraries can help. So Frameless can help you. These libraries I showed can help you. Sometimes we needed to dig into Catalyst internals to find out what is happening. Yeah, and one thing that you can face is this compile time overhead. Implicit resolution has a lot of stress on the compiler in Scala 2.12. It's 10% better in Scala 2.12. So we are waiting very for this Spark 2.4 that will have Scala 2.12 support. So that will be very, very good. And check out these open source libraries. That's it. Any questions?
Thank you, David. If there's anyone who has any questions, let me know and I'll bring the mic.
Hi.
Hi.
I'm from Neo4j, so we're also a graph database company. So I guess we're colleagues. And so you were saying on one of the slides, I think slide 26, you were investigating something. Let's see if you... Yes. So there on the type data set, you were able to achieve type safety here, but only if you knew the type at compile time, right?
Yes.
So you also mentioned you wouldn't be able to store arbitrary types, which the DataFrame API can do, of course, because the row is schema. I mean, the schema is it's not type safe, so it can have any number of columns called anything, right? But
yeah.
Here you actually have to have a case class with defined for all the fields.
Yes.
So how do you solve the problem with arbitrary types?
So arbitrary types mean that arbitrary JVM type. So arbitrary type that can appear on the JVM. And this can be solved by defining the encoder for that type. So as I mentioned here, whenever you are using a type that is not supported by Spark, you have to write this encoder for it. And that so that will determine the memory layout, and the layout it will look like in, where is it? Look like in Parquet or any of the stored formats. So basically, that's how you define an arbitrary type.
Anyone else have a question? All right, let's give a round of applause for David.